Good morning and welcome to our laser hardening and laser welding webinar today. My name is Dave Fitzgerald and I join you from Farmington Hills, Michigan at EMAG LLC. And I'm joined today by my colleague, Konrad Eibel, who joined us from Heubach in Germany. I hope you enjoyed today's webinar and we look forward to answering any questions that you may have. And now I'll hand you over to Konrad. Konrad?
Thank you. Hello. And welcome also from Heubach. We will show you today the laser as a highly productive and flexible tool. To make this for you as useful as possible, as Dave has mentioned, for sure you can you can give us questions online. You can use two methods, either in the live chat or with the anonymous question function that is also available. We hope we can answer most or all of your questions just to make it a good experience for you. So my name is Konrad Eibel. I've been working with EMAG for over 20 years now. For 9 years I've been in technical sales, and since 2 years I'm the head of offer engineering here at EMAG Lasertech. Yeah, we are in Heubach. This is 60 kilometers east of Stuttgart. We are one of the technology companies in the EMAG group. We have here in Heubach the ECM technology for electrochemical machining, and what we are talking about today, the laser technology, meaning Lasertech. Yeah, we will start with an overview of the EMAG Lasertech machine portfolio and have a closer look at the ELC6 machine. We will then use, of course, the opportunity here to show you our newly set up and updated laser application center, meaning we will do a tour and already see some of the machines from the portfolio in action. Then when we come back to the presentation, we will try to build the bridge from the machines and the technologies into full turnkey systems. And as Dave has mentioned, laser hardening will also be discussed with the machine type ELC 1300 LH. So this shows the EMAG Lasertech ELC machines. That means EMAG Laser Cell. We have on the left side the more universal, the more flexible machines, and on the right side the more component-specific machines. However, the distinction is not always black and white, meaning if a machine is shown here with these workpieces, it is also very well possible that other workpieces will fit onto this machine. For sure, if an inquiry comes for welding a workpiece or laser hardening a workpiece, we will look at the application and look to quote the fitting machine for the process. Starting on the left side, we have the ELC 160. This is our most often used machine. For the last years, there are almost 200 machines of that type producing parts around the globe. The machine is a linear design, meaning a workpiece spindle coming from the bottom is moving linear through the process stations. About 5 years ago, in 2018, we introduced the ELC6 machine to the market. And the big difference is this machine has a dial table for loading. That means, of course, load-unload can be done in parallel to the main process, meaning the cycle time will be optimized. Both machines are very well fitting for what we see here. These are passenger car powertrain parts, laser welding. And the ELC6 machine, and this is why we'll look into detail into this machine, has in this time quickly developed into our most important machine and the machine we quote and use the most today. Now the ELC 600 machine is here right in the middle. The name suggests it already, is made for bigger parts. That somehow makes it more component specific. However, not only truck differentials like in most cases, but other commercial car powertrain parts are very well suitable for this machine. However, it's in the middle. Why? Because it's still a very flexible design. The machine, let's say, is a big version of the ELC 160, so a lot of flexibility is there. Then we have the ELC 1200V, meaning 1200 parts with a length of up to 1200 millimeters can be welded here. And the design is vertical, V is for vertical here. The most applications are, for example, welding of these aluminum tubes to aluminum fittings, and those are used, for example, in air conditions. The machine is also dial table, and we'll see it in the laser application center in a minute. And it is the most simple machine that we have, but still quite flexible for simple applications. And then the last one being the ELC 1300 LH. This is for laser hardening, and the part length can also be up to 1300 millimeters. So these are the machines, let's say, for the main processes, being laser welding and in this case laser hardening. We also have machines for other processes such as laser cleaning and ultrasonic test. They can also be quoted as standalone machines, but in most cases they are used in a full turnkey system together with laser welding. So here we don't have a distinction. All these machines are quite universal. You see, the LC4 is suitable for all those passenger car powertrain parts. The LC8, being bigger, is more suitable for, of course, for commercial vehicle parts. And then the ultrasonic tester is made also for the same range of workpieces, those passenger car powertrain parts. Now a closer look at our most important machine. This is the ELC6. You see on the left side the view from the operator side, and on the right side from the automation side. And this is already the version for automated loading, which is what we use most of the time, let's say over 90%. But also available is a standalone version of this machine. For manual loading, this will then feature part of a safety fence and the necessary light curtain. A quick look inside the machine, and we can show this picture later on the tour also. We have position 1, the load-unload happens on the other side of the machine, which can be seen in this picture. But the dial table, position 2, brings the workpiece into the welding area. There, position 3, the work spindle clamps and locates the part from the bottom and brings it up top to position 4, the counterbearing, where the upper weld toolings are located. This whole counterbearing unit is also positioned on a slide unit, the U-axis, so different weld toolings can be put to the process depending what part is being produced at the moment. This is one part of the flexibility of the machine. The other part is, of course, the design of the welding head, or let's say the location of the welding head. It's mounted on an array of positioning axes, for example, a horizontal axis, a vertical, and a swivel axis. And of course, this gives further flexibility. Position 6 is then the supply units, for example, electrical cabinet. It is shown here standing at the machine, but for sure that position can also be adjusted, whatever the plant requirements are. So the ELC is a production laser welding machine for maximum output, designed for a compact footprint. It is fast, using that dial table for parallel load-unload to the process. The flexibility is given by the different weld toolings that are possible and the arrangement of the weld head. And the precision that comes from using our own customized clamping and locating devices, meaning everything there is coming out of one source from EMAG. Then regarding the quality control, meaning process safety, we have an active control system for the weld position, which we will be explaining in detail later. and also, of course, state-of-the-art process monitoring systems such as a laser welding monitor can be used. Economical reasons are, of course, the use of an efficient laser source, perfect energy input, and also the use of electric drives wherever possible instead of pneumatic or hydraulic units. And like I said before, it is a compact design and also designed that the supply units, the further supply units, can be positioned flexibly. Now we come to the Laser Application Center, which we have here. We have given this Laser Application Center a new look. We have made it look really nice in the last few months, but for sure there have also been quite some huge investments here. For example, what is shown on the right side, these machines concern the brake disc coating, or they are the coated brake disc technology. We have the laser cladding machine ELC 450 Duo LMD for coating the brake discs, and right next to it the VLC 450 DG for grinding those parts into tolerance. And at this stage I just want to point out quickly, about the middle of April there will be a separate webinar just for these technologies to go further into detail, but that would be just too much for today's webinar. We will focus on the other laser welding and laser hardening technologies which we can offer. We already saw those machines in the machine portfolio. That is the ELC 1200V. We have the ELC 160 and the ELC 6 for laser welding. And we have the ultrasonic tester. And now we will take the chance and have a look at the machines, some of which are in production. I have right now received a first question regarding our Laser Application Center. What test processing options are available? What lead times do you need for new workpieces? So for sure possible is laser cleaning, laser welding, laser hardening. For example, also processes like laser structuring, and of course the ultrasonic test. For all those technologies we can do first prototypes, we can support a process development, and of course make process validations. What lead times do you need for new workpieces? That depends. If it's only, let's say, a process validation of an existing process, it can be quite quickly. A lead time would be 2 to 4 weeks. However, if it's more work, let's say like a complete support of a process development, then I think 6 weeks lead time should be considered. Okay. Then we will start the tour now. The first machine, the ELC 1200V, our most simple welder, as you can see, rotary table design. Load unload is being done here in the front, and then the part, and then the dial table brings the workpiece into the work area. The machine is really fast. For example, the aluminum tubes we saw earlier, those were produced or are being produced at a cycle time of 6 to 8 seconds. Now, the machine is quite flexible, and to show this, actually here in the lab we have set it up for laser cleaning. Here you can see the scanning head. It covers an area of about 85 by 85 millimeters, and also this cleaning head is assembled on a system of axes. We have a vertical, a horizontal, and also a swivel NC axis here. And the laser type that is being used for this cleaning application is an IPG laser source, high pulsed, 200 watts of energy. Maximum energy input is a millijoule. Now we can demonstrate a live application here. We have painted the part with a black pen, and now we will try to remove this black paint with a laser. So the scanner head is put into position, then the part is rotating, and the laser will remove the paint from the surface. And you can see the result here. Of course, the left side has been cleaned and the right side is still with the paint on it. Thank you, Sigi. Then we will just have a quick look on the display here, and this will also be described more detailed later, but you can see already we are using our own EC scan software. EC stands for EMAG controlled, and we have quite some software applications that we are using for our own processes, again, to give the customer the benefit to receive everything truly out of one hand. So here are some more questions coming in. What is the time of retooling the cleaning machines? Keyword flexibility. In a usual setup, we have on the LC4, for example, installed 2 fixtures on each side of the table, meaning 4 fixtures in total. They are equipped with quick change interfaces, so the mechanical changeover is only a matter of a couple of minutes. 5 minutes are more than enough in most cases. And what about deep soiling or rust? Can this also be removed with a laser? We have had some applications where we have removed rust. However, if it goes really deep into the workpiece, a closer look has to be taken. There will be a physical limit. But easy rust, surface rust can definitely be removed. So now we come over to our next machine, our ELC 160. On the right side, you see the setup for laser welding. You see the weld head in the center. It is equipped with a 1:1.5 relation. That means if a fiber has a 200 millimeter core diameter, for example, the laser will be focused to a 300 micron. We're talking about micron, sorry. The laser will be focused to a 300 micron spot coming out of a 200 micron fiber. Different technologies are available, different laser sources, and also, for example, the bright line weld technology can be used. At the moment, the machine is set up for the laser hardening process, and for that we are using a different optics here shown on the left side of the machine. This is a PFO scanner head. PFO means programmable focusing optics, and we can now start a laser hardening process. So you only see a small spot. Again, the workpiece is rotating. The optics itself is standing still. The surface is being heated up to the austeniting temperature. So the structure changes to austenite. And then the workpiece cools down. And that way the heat is flowing away from the austenite, and that is enough. That heat flowing away is enough to have a self-quenching effect. And therefore we reach the usual martensite structure, which is intended to be the hardened surface. Okay, so I have already a question coming in. What hardening depth can be achieved with laser hardening? Typical values are from 0.2 to 1 millimeter. That will also be later on one of the slides from the presentation. Good. So we are trying to follow a bit from the logic, the process chain. We started with the laser cleaning, came to the laser welding, and what then in most cases or in a lot of cases comes is process control. In this case, the ultrasonic test, which is used as a non-destructive testing method. Here the workpiece will be rotating around a probe, and the sensor is located inside the part. And you see a bit of a water flow that is necessary because that ultrasonic sound cannot travel through air, but only through liquids or solid materials. That's why between the sensor and the steel, you always need a reliable water bridge. The result can then be seen. The result can then be seen on the screen here. So this gives a complete view of a B scan, we call it. That is then all the signals that are received by one rotation of the part. So the horizontal axis shows 0 to 360 degrees, and the vertical is of course the amplitude which the ultrasonic sensor registers. The red line then is the so-called gate, which is set during process development and needs to be defined. Everything that is over this red line is registered as a fault. And we see now here the faults that have been detected and the limits. What we want to point out is for sure, for example, the defect count and the limits. All of this can be easily set by ourselves, because if you look at it, it's also EasySonic software, meaning our own software for this process. So truly everything is completely made by EMAG here. Okay, so now we have seen the non-destructive tests, which can be done as 100% quality control. However, for sure, during all these processes, every now and then you have to really cut a workpiece and look what's inside. Has the weld really reached the intended depth, or have new problems come up? For example, has there been new cracks? Something like that. And for that, the destructive testing is used. So parts need to be cut and put under a microscope. For this, we have also re-equipped our laboratories. We have 2 rooms. In this room here, we do the cutting, polishing, and etching. So first, on this machine, we cut some slices out of the workpiece or some segments. It's required. Then we go over to the polishing, where we can use different levels of polishing the parts depending on the roughness. From very rough to more finer. And then it's almost ready, but in order to be able to see the contrast on the microscope, you also have to do an etching process. So this is being done then here. In this area, usually nitrile is used for steel parts, or for stainless steel applications. Yeah, for stainless steel applications, an etching liquid according to Adler, for example, is used here. This is typical. Okay, so now we have prepared the cut sections, and then we have to evaluate them. This is done in the next room. So here we have the microscopes for evaluation, and also on the other side, the hardness testers. So we get these, for example, those cut samples right here, and we put them under the microscopes and evaluate, do we have the right thickness, do we have the right structure. In this case, it's the coating of a brake disc, and we have a state-of-the-art high-tech Keyens microscope for this case. Goes up to a magnification of about 2000, and then we can really look into the material. Right here we see the base material, the cast iron, then we see the base layer, which is usually stainless steel something, and then we see the friction layer, the hard layer, which contains the red areas that are the tungsten carbides in this case. So we can really evaluate this. And for this, the microscope has a so-called LIPS function. That is a fluorescence method to really analyze the materials or the elements that are in the material. Here are then some more microscopes. This one is a simpler video microscope. Scope for optical analysis of the parts. Then the applications for sure, laser hardening or this coating of the brake disc require a hardness test, but for sure also a normal laser weld. You also have to do, let's say, 10 hardness test points across the weld seam to also be able to evaluate the heat influenced zone of the weld. And for that we have the two weld hardness testers here, the second one being a more simple version and the first one being able for automated hardness test series. Okay. So now we're going to take a look at the ESC6 machines in real time. There's not so much to see right now because the machine is still in build, but I still want to show the great accessibility of the machine. Right now I'm really standing in the machine. I can reach everything perfectly. This is great for maintenance, great for setup and changeover activities for sure. And we can also look again at all the units we saw earlier on the presentation. Of course, the main spindle coming from the bottom, clamping, locating the parts, bringing them up against the counter bearing, which is here. And you can see the different counter bearings that are installed. So that is part of the flexibility. That whole thing is, like I said, a slide unit, that whole upper rack. And then here we have the weld head itself. And this weld head is also positioned on a system of axes. We have a horizontal one, of course, a vertical one, and a swivel axis for further flexibility. All right.
Conrad, we have a question for you.
Mm-hmm.
So it's about the laboratory equipment you just showed us. How much effort is required for process reliability? And is the laboratory equipment necessary for every customer in order to receive good welding results with laser welding?
Mm-hmm. So how much effort is required for process stability? That depends. If we only do a process validation, then a couple of days is usually enough. However, if we go further and have to support, let's say, a process development, then you should start with about 2 weeks until everything is done, or maybe 2 rounds of 1 week or something like that.
Okay, very good. Thank you.
And the second, this lab, so I think that is regarding the equipment from the lab, meaning cut, polish, etch, and microscope. And the answer is yes. If you have a laser welding process, sooner or later you will have to do this. So everybody who really does this and produces these parts in large volumes needs that equipment. Okay, so we are back from the tour of the Laser Application Center, and I really want to point out again, it's been made to look nice, that's okay, but really you see massive investments have been done here to bring this up to date, to have a real powerful center here. And we have, in the department, we have 8 highly qualified colleagues working on those processes, either developing them, improving them, and most important, getting them ready for a mass production scale. This is of course what matters here. And so this is really one of the tools we can use to produce and to deliver full turnkey systems. I will first give a couple of examples for these turnkey systems, so you know what I'm talking about. The first one is out of an electric drive from a passenger car. It's the rotor shaft. It's a 2-piece design, so you see the processes on the bottom. The system, but I will go through the processes anyway, and we'll also look at a video. So the system looks like this. There's load unload on a pallet conveyor on the left. Then the parts are taken by a gantry first to the laser cleaning process and then to the ELC6 laser welder. But in this machine we also do the pressing of the parts together. We do the preheating of the parts. We then do a seam position control and also of course the laser welding itself. And then the parts go back to the pallet conveyor. This is the video. On the left side you see the single components, and on the right side the finished welded parts. Here comes the gantry, picks up the single components, brings them to the laser cleaning machine. There the weld area is cleaned on the one component and then on the next one. Organic substances are removed because these can lead to problems in the weld area. Now the cleaned components are taken to the ELC6. First, the last welded part is unloaded, and then the single components are being loaded to the dial table. Of course, at the same time, on the other side of the machine, a part is welded. This is now finished, so the new part comes in, and we have to look quickly because the joining process is quick. It's already done, that's it. Now comes the preheating, necessary because of the high carbon content of the workpiece. Again, to avoid cracks or other problems. And now we have length tolerances and heat in the part, so we really have to do a seam position control, meaning we really have to determine where to weld. And this is being done. For sure we'll take a closer look at the seam position control later. But now the part is readily welded, transported back to the gantry. Welded part goes out. New part comes in. And the finished part goes back to the pallet conveyor. The second example is also out of electric drive, out of e-drive. And this is a system we will show for which is able for welding differentials and intermediate shafts. Both these parts go together in a lot of those drive units, and both those parts can be welded on the same system. And if it's designed right, then it will be not necessary to have any manual changeover for both those parts. Again, the process sequence is shown on the bottom, but we have it also here. The system looks like this. Here you see again the components which we showed in the beginning out of our product portfolio, the LC42 for laser cleaning, the ELC6 and the ultrasonic test. The parts arrive or are being loaded to the pallet on the left side. Then they go to a DMC check. Then they go to the LC42 for laser cleaning. Then they go to a cross shuttle for the press process. On the other side, they are moving upwards to a runout test and then downwards to the ERC6 for welding. Next is the brush station to remove some smoke from the weld surface or some loose spatter. Followed by the ultrasonic test. And if everything is okay, we go through a laser marking station back to the unload area. And we also have a video of a very similar system for you. In this case, not for a differential, but for an intermediate shaft. Out of an E-drive as well. Left side single parts, right side welded parts. Here the parts come in. DMC is being checked. Then the parts are being loaded to the laser cleaner. And here again, the weld area is being cleaned. First on the gear and then on the shaft. Then the parts go back out, are unloaded by the gantry. And they go to the press shuttle in the pre-press position. The press force is applied from the top. Of course, the process is force and path monitored. In this case, we didn't have a runout test, but we have an induction preheating. Again, because of the carbon content of the workpiece, we rotate it for a constant heat distribution in the part. And then the part goes quickly to the laser welder. In this case, the ERC 160 machine. Spindle clamps and locates it from the bottom, brings it into the weld station, locates it against the weld tooling. You don't see much. This is okay because everything is covered. That is good. Only the weld area is left open. And on the lower right, we see the process monitoring system, the LWM system for process control. Then the part is unloaded, flipped over and brought to the brushing station. Part is rotating, brush is rotating. And then it goes to the ultrasonic test station. The part is being loaded to a spring-loaded fixture. It is then pressed down to have it arranged completely correctly in the gripper and then also rotated around a probe. Now it's a bit wet, so we have to do a bit of drying, rotating the part and using blow air before it is unloaded as a finished part. So,
Conrad, we have a question for you.
Yeah.
Why do the parts still need to be cleaned before welding? They're already coming clean from pre-machining operations.
Not always. Even if they come from, let's say, a turning process, there might be some cooling residuals or cutting fluid residuals on the surface. And even if they come from a washing machine, some residuals from the washing process might still be on the surface. And those organic substances will not give you a good weld. So this is why it's absolutely recommended to do the laser cleaning. And for example, in differential welding, about 90%, almost all the inquiries we see have specified that the laser cleaning needs to be done before the welding. Okay, so now to sum it up, we're talking about, or we were looking at some full turnkey systems. So what makes EMAG LaserTech turnkey system special? Now, what we do is we combine the machine tools, the custom clamping equipment, and the custom automation. All of this is in our hand completely, truly. The clamping and the automation is completely designed here, manufactured here, assembled here. And, of course, and this is why we took this close look at the Laser Application Center. We have the technology, the processes, to prove the process, to make sure everything runs smoothly before we deliver the machine. And further to point out, last but not least, are the EC applications, those EMAG-controlled software tools. We have some of them shown here, and this really makes the system complete and a true turnkey system. Everything comes, let's say, out of our software department. If there's questions regarding this, if there are some problems in the software, no need to talk to third parties. EMAG handles it. So we will take a look at some of these applications. First, we saw this earlier in the rotor shaft welding. The EC seam is a complete system for weld precision control. So the laser line generator projects a laser line across the weld seam area. And exactly where the weld gap is, and a slight chamfer is needed, 0.3 millimeters. This laser line will be monitored with a camera through the lens, and this chamfer will be registered and measured exactly. And this will give the information. This will give then the information to the welding process if an adjustment of the weld head during the process is necessary. So, first step, the measuring cycle. Second step, we do the internal evaluation using our EC seam software. And then this data is being transmitted to the weld process, to the weld head. So we can do an active weld tracking, and there are actually two possibilities. Let's say the quicker one, the more simple one would be just a seam position correction. You do this measuring cycle, you determine one correction position, the weld head moves to that position prior to the welding process, and then stands still during the process. However, you can also do a full seam position control. So the path that is being calculated of up to 20 points can then during the weld process be precisely followed by the weld head while the workpiece is rotating. So we are sure to always weld in the exact correct position. So then we come to the EC Sonic application. First, there's another question.
Yes, Conrad, if I can interrupt. Does the EC seam have a negative effect on the process time, or does it run in parallel to the main time?
So we have seen the 3 cycles, let's say, or the 3 steps of the EC seam. So you first have to do a measuring cycle, and then that will take, depending on the workpiece diameter, of course, that will take 2 to 4 seconds. The other 2 steps, however, have no influence on the cycle time. But yes, for the seam tracking, of course, but that is the same with every one of these systems. You sure have to establish the path before you start the welding. Okay, back to the EC Sonic application. Again, we see here on the top, we see the B scan, meaning this is one track around the part, 0 to 360 degrees, and wherever the color changes from the blue, something has been registered. And on the amplitude chart, you can also see how high that is, and most important, how wide. Again, we see the red line where the gate has been set. Everything under that doesn't count as a fault. Everything over it is a fault. And there you see it also. This comes out of our software. On the picture above, you see 3 faults have been counted. 5 would be allowed. This depends then on the ultrasonic test specification by the customer, for example. So in this case, 5 are allowed, 3 have been detected, result is okay. The biggest single fault was 1.2%. 2% would still be okay, so check. Then, and the sum of all the defects that have been detected as defects is 2.3%, and 5% would be allowed. And to show you that, it's quite easy to change these parameters in our software by ourselves. This is even easy for the operator themselves. It's a very, very nice display, very intuitive, so the changes are made easy. Easy Join software is for press process control. We have on the vertical, we have the press force, and on the horizontal, we have the path that is being registered. And you see here the real curve that has been done. And of course, this curve has to pass through a certain process window, meaning a rectangle shape somewhere here. And if it passes through that process window, then it can be rated as okay. Why we are showing this display right here is, you see already the workpiece ID, so we connect or we link this process data to the workpieces. And in order to manage all this process data, we have the Easy Data system for process data collection and organization. So it can, for example, later be passed on to a plant MES system. Yeah, we have here. And the system is also designed really easy, really intuitive. You can just change. This is now the process view. So you can change here between processes, different processes. Now, right now, second laser cleaning is being chosen. Here you see the single workpieces that were being checked or that were being cleaned. Sorry, you see they were done in place number 1 or place number 2, and you see in this case all of those parts were done with 148 watts of power. Another example. This is now not the process view, but let's say the part view. So position number 1. You have the search function to look for the different parts. Number 2, then you can choose those parts. And in number 3, number 2, you can choose which part you want to look at. Here then you see in the display all the different process parameters that have been recorded for this part. And even then in 3, you can switch around between the different process plans, meaning different work pieces, or even different batches.
Yes, Conrad, we have another question about the inspection systems that we offer. Do we offer ultrasonic inspection systems as standalone units or standalone products, or are they only sold as a combination with our laser welding systems?
Yes, we also offer the ultrasonic test machines as standalone products. Most of the times they are included in a full turnkey system, but also available as standalone.
Thank you.
Okay. So to sum it all up again, we use the machines, the tooling, the automation, the processes, including the software, to really build for our customers a true turnkey system out of one hand. Now to go into laser hardening also, we saw it already in the application center, but this gives an idea of the flexibility which is possible with the laser. We can harden just this surface, then we harden the cone here, we harden that groove, whatever is required right here on that HSK tool holder. So flexibility is great. And of course these other gets more simple with the next work pieces, so that's not a problem. And the machine we used here was the ERC 1300 LH, is shown here. Of course, again here, big opening door, a big sliding door, great access for the operator. They will love it. They are really standing inside the machine, inside the process. And again here we have the workpiece will be on the bottom rotating. And on the top we have also a PFO scanner head, which is in this case located on 4 NC axes. So 2 horizontal, 1 vertical and 1 rotation axis. And that even made it possible to harden from the side and reach the inside of that tool holder. Here's another look at the machine. See the great access again. And those supply units which are standing here on the side, just to show them they are also flexible in their position. So whatever the plant requirements are, they can be put somewhere, of course, somewhere close to the machine, but the position is flexible. Now the laser hardening process itself, we talked about a lot of these points already. What happens? So a high power laser beam is moved across the workpiece surface in the feed direction. And additional to that, it's also being scanned rectangular to the feed direction. So a line is created. That is typical between 5 and 30 millimeters of hardness zone. The surface goes to the austenite state. The workpiece cools down the heated zone, and that is enough to have that self-quenching effect and reach that hardened surface, the martensite state, which is intended. Furthermore, typical hardening depths go from 0.4 to 1 millimeter, and a hardness of 60 is possible. And here is a summary of the laser hardening advantages. We saw it already. Self-quenching, we don't need cooling media. Then we have a very precise energy input with minimum heat influence by the laser, and reduced throughput times can be reached thanks to integrated processes. So this machine here, C1300LH, will fit very well into a usual production line for these parts. In other hardening processes, it might be necessary to move the part away from the line or even to a different supplier to do the hardening. In this case, can be integrated. So you save a lot on logistics, of course. Then, regarding quality, we have, of course, the high repeat accuracy thanks to that scanner head and those NC axes. We have the precisely controllable process by using temperature control. Pyrometers are used. And the low energy input, the precise energy of the laser, leads to low distortion and low hardening stresses. Way lower than with the other hardening methods. And then the flexibility, of course, we've discussed about this already. Specially defined functional surfaces can be hardened. Complex 2D, 3D geometries are not a problem. And even contours or geometry that is difficult to access, for example, the internal hardening, can be done here.
Conrad, I have one last question for you, if I may.
Sure.
Can we achieve similar strengths and hardness with laser hardening as we would with, say, the salt bath type application?
The answer is yes. We can go up to 60 Rockwell. We saw that. And in one application, a salt bath hardening was replaced by laser hardening for our customer.
Very good.
All right, good. So to sum it all up a bit again, to give you a structure overview what we talked about the last 50 minutes. We started with the machine portfolio overview, took the tour of the laser application center here in Heubach, and then discussed what makes EMAG full turnkey system truly unique, everything out of one hand. And we finished up with the laser hardening process. So if there are no further questions right now, That's it from my side.
Thank you,
very much.
Conrad. Thank you, Conrad, and thank you all for joining today's webinar. We certainly appreciate it. Hope you enjoyed and learned something new today. We would welcome any questions that you may have, or if maybe you have some application you would like us to take a look at, we'd gratefully take a look at those for you in more detail. So please feel free to reach out to us. And again, thank you again for joining us today.
Thank you for your time.